Hi everyone. Today we are going to cover section 5.4, which deals with optimization. So basically optimization is when you have a quantity, it's how to minimize or maximize that quantity in order for you to achieve like the best or the optimum results, right? So for example, it's, what is the maximum amount of, let's say, items you can sell in your factory or you can produce in your factory to make the most profit. And you might be thinking, well, that's easy. The more of a item I make and sell, the more money I'm going to make. Well, that's not necessarily true, because once you get past a certain threshold of how much of the item you're making, then you have to think about, okay, now you have to hire new employees, for which you have to pay a lot of money as salaries, or your employees have to work overtime, so you have to pay them, right? So there is a point after which it doesn't necessarily make itself like cost effective, right? So that's pretty much what optimization is. Okay, so getting down to what we're going to be doing in this lesson though, how is it that when we're faced with a word problem like this, how are we going to solve it? Well, the first step is to understand the problem, and that might seem like a very trivial thing to you, but really what this is about is identify what it is that you're given and exactly what it is that you are asked for, because that's going to be the key to everything else later, right? So once you figure out what you're asked for, you have to develop a mathematical model for the problem. Now in math, when we say model, it's not an image. A model is basically an equation. A mathematical model is an equation. So first you have to develop that equation. To do that, diagrams might be extremely important. You have to introduce a variable to represent the quantity that needs to be maximized or minimized. And then you need to write a function. For that function, it's absolutely important to find the domain, so that, now you're actually talking about like real life things. So you have to have values that make sense, right? You can't be producing, negative 2,000 desks or chairs in your company. And then the nitty gritty is just what we've been doing this whole time. Find critical points, endpoints, and then solve the equation. Okay, the last is to interpret the solution, and here's where you really have to ask yourself, does my answer make sense? Okay, all right, so let's start. We're going to focus in this class on basically three main types of problems. The first one is like example 1 here, where you have two numbers that have some sort of relationship, and you want to find the two numbers. So take a look at this problem here. It says find two numbers whose sum is 20 and the product is as large as possible. Okay, so talking about understanding the problem, you have to identify what it is that you want to be a maximum or a minimum. So here we want the product to be a maximum, the product to be as large as possible. So everything we're going to do has to involve the product of these two numbers. Okay, let's first get the two numbers, okay? We need to introduce variables. So we say, let x be the first number. Okay, how many numbers do we have? 2, x and y. And we know that the two numbers have a sum of 20. So x plus y is 20. So if x is the first number, then we need to solve this for y in order to see what y is, because that's our second number. Well, here y is 20 minus x. And so that is the second number. So now we are going to focus on x and 20 minus x. Those are our first and second numbers. Okay. What is the domain of this problem? Remember, what is it that we're looking for? We're looking for two numbers. So in the end, when we solve this problem, we're going to have, okay, first number is this, second number is this. So what's the domain for these numbers? Can any of the numbers be 60? No, because the two of them have to have a sum of 20, right? Okay, so the domain is from 0 to 20. We're going to assume positive numbers always for this, right? So the smallest the number could be is 0, and then the largest it could be is 20. Okay, now that we do this, the next part is to develop a model for this, right? In order to write your equation, you have to go to what it is that you are maximizing or minimizing. Right now, we want the product to be as large as possible. So when you write the function, it has to be for the product of these two numbers. So the function is f of x. It has to be in function notation. It's the product of these two numbers, means it's x times 20 minus x. First number times the second number. Here is pretty much where the bulk of that difficulty of the problem is over. Okay, now it's just a procedure like we did in the last two lessons. Okay, once you have this, we want something to be a maximum, right? Well, how do you find maximum? You have to take a derivative. So let's just distribute this so it's easier to take a derivative. And this is what you have to find the maximum of. This is what you need to maximize. To find a maximum, we take a derivative. So f prime of x is 20 minus 2x. Set this equal to 0. So x is 10. That is my critical point. Okay? Now, if you don't believe me that that's going to produce a maximum, let's try it out. Let's put this on a number line. We have a closed domain from 0 to 20, and 10 is here. And this is f prime, remember? If I take a number here, like 5, and I plug it into my f prime, that's going to be a positive. And if I take something like, 15, that's going to be a negative. So you can see that f is a maximum at x equals 10. Okay, so what is this? It's x equals 10. And remember, x was the first number. So if the two numbers together add up to 20, what would the second number be then? Also 10. Okay, so those are the two answers, 10 and 10. Okay. All right. So remember, find a relationship between the two numbers, figure out what it is that has to be a maximum or minimum, and write an equation for that. It could be the product of the two numbers. It could be, the product of one number and the square of another number. You have to rely on your algebra skills for that one. Okay, let's move on. So this is the second type of problem that we're going to focus on in this class. Basically, you have to make an open top box by cutting squares of length x from the corners of a 10 by 16 sheet of tin and bending up the sides. So initially, this was just a rectangular sheet. Okay. The entire length here was 16, and this was 10. Now what I did is I have cut out squares of length x. So basically I cut out a square of length x and x here. And here, these are all x units long. So how much did we cut out from the initial 16? I cut out one x here and another x here. I cut out two x's, so now this became 16 minus 2x. And similarly, this was on the bottom, had an initial length of 10, now it became 10 minus 2x. All right? When we fold up the sides of that net, is what we call it, you get a box with an open top, kind of like those donut boxes, like this. Okay, so now the sides here are 10 minus 2x and 16 minus 2x. Or let me do it to scale. Okay? All right, so let's continue. What is it that the problem is asking for? It says, how large should the squares be to make the box hold as much as possible? Okay? So if we want it to hold as much as possible, that's volume. That means we want the volume to be a maximum. Okay? And then it asks for what is the resulting maximum volume. Okay, so we have a box. What should X be in order for the volume to be a maximum? If we want the volume to be a maximum, now we have to come up with the volume of this box. So remember, volume is length times width times height. Okay? Length times width times height. So here, the length is, this is V of X. The length is 16 minus 2X. The width is 10 minus 2X. And how much is the height? The height is this, which came from the part that we cut out, so it's X. Okay, so that's the volume. That's the expression for the volume. That's what we need to maximize. Okay, before we can take a derivative of this, you have to multiply out all of these. So if we first multiply the first two parentheses, we get 160 minus 20x minus 32x plus 4x squared times x. Multiplying out further, 160x squared. And then I combine this to negative 52x squared plus 4x cubed. Okay, so now I need to find the maximum volume. To do that, I need to take a derivative. So let's go ahead and take a derivative. Sorry, this is just a 16. I'm sorry, I wrote that wrong. This was supposed to be 160x. Okay, so let's take a derivative. I get 160 minus 104x plus 12x squared. Okay, now I can factor out a 4. I'm going to factor out a 4, but I'm also going to write it in decreasing order of exponents. So change the order a little bit. It's going to be 3x squared minus 26x plus 40. Okay, so that's v prime of x. Now we're going to set this equal to 0. But to do that, I need to factor that polynomial. All right, so we're going to get 3x and x. And what are the two numbers that give us 40? And then it's going to give us negative 20x when we FOIL. So it's going to be negative 20 and negative 2. Okay, you can factor in whatever method you're comfortable with. So now x is equal to 20 over 3, or x is equal to 2. Okay, let's talk about domain for a little bit. All right, let's come back to our original box here. All right, I'm going to erase some of this stuff. So the idea is the initial box, remember, like the initial sheet was like this. And this whole red side on the bottom had a length of 10. And so now I'm going to cut equal sides from both ends, right? So suppose I cut 1 inch from the left and 1 inch from the right, and then I could do 2 from the left and 2 from the right, 3, 3, 4, 4. 5 is the most I can cut, because if I cut 5 from the left and 5 from the right, then I've exhausted the entire length, right? So I can't cut out anymore. So x, which is the length of how much you're cutting from the edges, x can only go from 0 to 5. So that's your domain. And so now when we look at the critical points that we got, x equals 2, that's fine, but 20 over 3, that's 6 point something. That is not in my domain, so I need to throw it away. Okay, so let's go back to the initial question. It says, how large should the squares be to make the box hold as much as possible? So the answer to that question is the squares have a length of 2, so they are 2 inches by 2 inches. The next part of the question is asking, what is the resulting maximum volume? So what is the volume when x equals 2? That's V of 2. And so we're going to put it in the original V, which is where? It's right here. Okay, so V of 2 will be 16 minus 2 times 2. 10 minus 2 times 2 times 2. So V of 2 is 144 inches cubed. Okay? All right, so you have like a very similar problem to this in the homework. Make sure you go back to this, mimic. The sides here for the box problems are always going to be the initial length minus 2x, the initial width minus 2x, and x here. It's always going to be in that formula, right? So you can blindly do it. If it's like 12 by 22, then you do 12 minus 2x, 22 minus 2x, x, every single time. Okay, let's move on. The third type of problem we're going to do is when you have a rectangle within another shape, like this one. So this says a rectangle is to be inscribed under the curve y equals 9 minus x squared in the square root. Let's talk about this for a minute. Now is the time that I want us to all sort of memorize that when you have this format for an equation, this represents a semicircle. And so how do we figure out that it's a semicircle? Basically, when you have y equals the square root of a number minus x squared, that's always going to be a semicircle. The square root of 4 minus x squared, the square root of 18 minus x squared, the square root of 25 minus x squared. And the radius is always going to be the square root of the number. So for example, here the radius is the square root of 9, 3. So look, I've graphed it here. This is a semicircle with a radius of 3. Okay, the problem is saying that there is going to be a rectangle inscribed under this curve. Inscribed means the corners of the rectangle have to be touching the semicircle. So here is one example of a rectangle I can draw under here. It's got to be from the x-axis up because the graph doesn't exist below the x-axis. And you see how the corners touch the graph. That's what inscribed means, right? And so the rectangle can take on many forms. Like it could be a narrow rectangle, it could be a much wider rectangle, right? The question is asking, what should be the dimensions of the rectangle with the largest area? So what are we looking for? We need the dimensions, length and width, in order for the area to be a maximum. Okay, so if the area has to be a maximum, then now I need to figure out an equation for the area of the rectangle. Well, luckily we know how to find the area of a rectangle. It's base times height. So let's figure out what the base of this rectangle is. Okay, this is the base of the rectangle. Now, in order to figure out the base of the rectangle, you're going to do the same thing every single time. The way in which we measure it is, If the rectangle stops here at whatever x value, then what's the distance from the origin to that? Well, that's just x, right? Whatever x value it stopped at, that's that length. So if it stops at x equals 2, then that purple part is 2. If it stops at 2.3, then the purple part is 2.3. So basically, we're always going to label that part as x. Okay? So then, how much is the entire red base? It's twice that, 2x. Okay? Now, for these problems, that base is always going to be 2x. Okay, because we always start from the origin out. Okay. Now, what about the height? The height is this. Okay. Because this is inscribed, because that vertex always touches the graph, no matter where your rectangle is, the height is always going to be the distance from the x-axis to the graph. X-axis to the graph. Another way to say that, because it's going to the graph, is this is always going to be y. Okay? Always going to be y. Right. So now, let's write that down. A of x is equal to the base times the y. But what is the y? It's this function. Okay, so again, whenever you have a rectangle inscribed under a function, it's always going to be 2x times the function every single time. Okay, since this is what we need to make into a maximum, we want to take a derivative of this. So let's write it in a way that is more conducive to derivative. Okay. So now, product rule, right? This is u, this is v. Let's do it. So u is 2x, u prime is 2, v is 9 minus x squared to the half, v prime is 1/2. 9 minus x squared to the negative half times negative 2x. And now 1, 2 cancels with 1, 2. So let's see what we have. A prime of x is equal to, so the first direction here is going to be negative, right? So I'm going to combine these two. So look, I have 2x here and another x there. So negative 2x squared. 9 minus x squared to the negative 1/2 plus 2, 9 minus x squared to the 1/2. Okay, and now look, we have a lot of factoring to do, right? This is why we kept solving all those problems before with all the factoring. So what can we take out of this? Let's take out negative 2. 9 minus x squared to the negative half. Remember, we take out the one with the lower valued exponent. So we have, from here, I just have x squared left, minus, because we're taking out a negative, right? We're factoring out a negative, 2, 9 minus x squared to the 1/2 minus negative 1/2, okay? Remember, that's how we did the factoring there. So this is going to be negative 2, 9 minus x squared to the negative half. And then what do we have here? X squared minus 2, 9 minus x squared. So let's see what we have now. Negative 2, 9 minus x squared to the negative half. I'll move that down in a minute. And then here I have x squared minus 18 plus x squared. Oh no, sorry. I had factored out the 2. Oh no, so it's just a negative. So minus 9 plus x squared. Okay, so let's see what we have now. Negative 2 stays up here. 9 minus x squared to the half comes down. And then here, I have 2x squared minus 9. Whew. Okay, so that's a prime of x. Okay, so what are the critical points here? Okay, let's talk about domain for a minute. So domain, remember x was this length at the bottom? Well, how big could the biggest rectangle be? It could go as far as like a 3, right? So the domain is from 0 to 3. So let's see how we can find critical points here. Remember, there are 2 ways to find critical points. The first way is to set the numerator equal to 0. So x squared equals 9 over 2. Take a square root. X is plus or minus 3 over root 2. From the denominator, 9 minus x squared to the half is 0. 9 minus x squared is 0. So x is plus or minus root 3. Okay? I'm sorry, plus or minus 3. Oh my goodness, I'm getting hungry. Okay? So x is plus or minus 3. So that we're not going to use because it's the endpoints of the domain. So what we're going to, one thing I should have mentioned is the domain is, it's not including 0 or 3 because, you can't have a length of 0 and it can't be 3 either because then there won't be any height to it. So the only critical points that we can use are this one. Can x equal negative though? No. So the only x then is 3 over root 2. So what are we going to write down for the dimensions of the triangle, the rectangle? Okay, so if x is 3 root 2, then how much is the height? What's the base? The base is 2x, which is 6 over root 2. And then how much is the height? The height is y, which is the square root of 9 minus x squared. 9 minus, what's x? 3 over root 2. When you square that, you get 9 over 2. Okay, so let's see how much that is. 9 minus 9 over 2 is the square root of 9 over 2. So the y is 3 over root 2. So the dimensions are 3 over root 2 by 3 over root 2. And then what is the largest area? The area is base times height, 9 over 4. I'm sorry, 9 over 2. So that's how we do this one. I know it's a lot, but again, for the homework, you do have a problem or two like this. So just mimic, find that, remember, the area is always going to have the same format. Base times height, 2x times y. From that, find the derivative, find the critical points, and then you can generate x and y. Okay, so the homework is due next class, and we do have an extra day to spend on this next time, so we can go over some homework questions then. Okay, thank you very much, and have a wonderful day.